complex numbers are so convenient for applying geometric transformations like rotation, scaling, and translation in 2 dimensions that you kind of like to find something similar that works in higher dimensions, for example, 3 dimensions. Hamilton thought a lot about this problem. Hamilton was kind of a prodigy. He learned Latin, Greek, and Hebrew by 5, and by 10 he'd learned a total of 12 languages, including Persian, Arabic, Hindustani, and Sanskrit. Now, he'd been puzzling over the issue of how to go beyond 2 dimensions using something like complex numbers for a long time when inspiration hit him, and he came up with these equations. Unfortunately, the time he came up with these equations, he was on a walk with his wife, and he was so taken with the idea, he wrote down the equations in the most convenient place, which was the stone bridge he happened to be passing. For this act of vandalism, in fact, there's a plaque on the bridge commemorating it. Now, as you can tell from this quote, Hamilton was not a modest guy. He thought this was the solution. And it is very convenient. The numbers that you get in this way are called quaternions, and they're still used today. But there's another concept that's used even more frequently, and that's due to Gibbs. Gibbs was a Yale man, started at Yale at age 15, and eventually became a professor there. He had an idea, vector analysis, that displaced quaternions for a lot of applications. Now, he didn't publish his notes for a long time. Finally, he published them 20 years later. And he wasn't a complete hit. There are those who still believed in quaternions. For example, Peter Guthrie Tait, who was a supporter of quaternions. But even though quaternions are still used today, vectors are used much more. So what's a vector? This is what you might think is a vector. A list of numbers, in this case 4 numbers. This is called a 4-vector over the field of real numbers. We'll use Python's list sometimes to represent vectors using this notation. And the set of all 4 vectors over the real numbers is written R4. This notation might remind you of the notation R to the D, the set of functions from D to R. And in fact, I want us to think about vectors as functions. So our 4-vector you might think of as a function from 0, 1, 2, 3 to the real numbers. F to the D is notation for the set of functions from 0 through D minus 1 to F. Here's another example using the field of GF2. GF2 to the 5 is the set of all 5-element sequences made up of zeros and ones. So, for example, 0, 0, 0, 0, 0. Here's another example. Let words be the set of all English words. Now, in information retrieval, a popular way of representing documents is to forget the structure of the document, forget the syntax, and just represent the document by a bag of words. That is, a mapping from the set of words to the numbers, specifying for each English word, if the document's in English, how many times that word occurs. So we're often going to use Python's dictionaries to represent functions. So, for example, this is the function that represents the vector we just talked about. What about representing a document, that is, a word bag, a function from the set of all English words to the real numbers? Well, this representation starts looking not so good because there are a lot of English words and documents don't tend to include them all. We adopt the convention that key value pairs where the value is 0 can be omitted from the dictionary. So the document, the rain in Spain falls mainly on the plain, would be represented by this function. We haven't represented those words that don't occur in the document. A vector, most of whose entries are 0 is called a sparse vector. And if no more than k of those entries are non-zero, we say the vector is k-sparse. A k-sparse vector can be represented using space proportional to k. So, for example, when we're using this bag of words model, we can represent all the documents in a corpus of documents, and the total space required is no more than the sum totals of the length of the documents. Now, most signals acquired using physical sensors, such as images or sound, are not sparse coming in. But there are ways of achieving a sort of artificial sparsity by suppressing some of that signal. That's the idea of lossy compression, and we'll get to that later in the course. So what can we represent with vectors? We've already seen we can represent documents. We can represent binary strings, and this will be useful in cryptographic applications. We can use a vector to represent a collection of attributes. For example, the voting record of a senator, or the demographic record of a consumer, or characteristics of cancer cells. We can also use it to represent the state of a system. For example, the population of different countries in the world, or the number of copies of a virus in a computer network, the state of a pseudo-random number generator, or the state of a game called Lights Out. You can also use it to represent a probability distribution, which is, after all, a mapping from some set to the real numbers. Here's a way we can use it to represent an image. An image, you ordinarily think of an image as a grid of pixels, and each pixel is represented by an intensity. Well, you can think of this as a mapping from the pixel coordinates to the real numbers. So this image is represented by this function, which we can interpret as a vector. We can also represent points in space. This is one of the original uses of vectors, so we'll be taking a closer look at this application. We saw that complex numbers can be represented by points on the plane in such a way that we can carry out geometric transformations in a simple way. We're going to use vectors to represent points, and we'll see how these same operations can be represented using operations on vectors. Let's try this in Python. Let's start with a list of vectors represented as lists of length 2. We can plot these using the same module we used to plot complex numbers.